Okay, this chapter we're going to be working on rational functions and equations. We're going to start out with a quick review over simplifying radicals. So here, we're going to start with this idea of perfect squares. So you know what perfect squares are. So numbers like 1, 4, 9, 16, 25, and so on. So, of course, perfect squares come from 2 being squared, 3 being squared, 4 being squared, etc. So if you can list out some more of the perfect squares, this next one will be 7 squared, which is 49, 8 squared, 64, 9 squared, 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196, 15 squared I think is 225, and that's about all that I know. Okay, so if you know other numbers that are perfect square, that's great. You really do want to know like 1 through 169. Those should be numbers that you recognize pretty immediately that are perfect squares. Okay, so if something's not a perfect square, how do I simplify it? Well, do a factor tree. So 400, that's not a perfect square. So I would probably go 4 and 100. Now there's a couple of different ways you can do this. Now these are both perfect squares. So I know that the square root of 4 is 2, and the square root of 100 is 10. So 2 times 10 is 20. Sorry, I said the wrong thing. 400 is a perfect square. Square root of 400 is 20. Okay, however, if you don't know that, you can do your factor tree. Now, I stopped when I had perfect squares here because I knew what the square root of 4 and what the square root of 100 was. But if you don't, or you don't split it up in that same manner, you could always take it all the way down to prime factors, and then you can do groups of 2 things at a time. So if we did that, I'd have here I'd have a group of 2's, then I would have another group of 2's that go together, and then you can see I'd have a group of 5's. So a group of 2's, another group of 2's, and then a group of 5's, and then that also gives you 20. Okay, so let's go to example number 2. 48 is not a perfect square. So factor tree, 48 is going to be 6 times 8. 6 is 2 and 3. 8 is 2 and 4. And then your 4 is 2 and 2. So again, you're finding groups of 2 things that match. So I have 2 groups of 2's. So a 2 would come out, another group of 2's comes out, but then here that 3 does not have a partner. So it's going to stay under the radical, and then we would have 4 root 3. Okay, multiplying radicals together. You can multiply them together. So 10 times 12 would be 120, so square root of 120. Okay, however, that's not a perfect square, and I'm just going to have to do a factor tree on 120. So instead of putting that together as one number, I would just say, okay, I'm going to do 10, and I got to do 12. And then I know that 10 is 2 times 5, and then 12 would be 4 times 3. Now you can break that 4 down into a 2 and a 2 if you want to. So we have 2, 5, 2 2's there, and a 3. So once we are at our prime factorizations, well, a group of 2's is the only thing that I have that I can take out. So 2 is going to come out. 2 times 5 times 3 is going to be left over inside the radical. So that's 30. Okay, now you could do the 120. I'll just do it over here to the side. So, I mean, you certainly could multiply those 2 things together, do the 120, and then start doing your factor tree from there. I just kind of did that same concept, but I just left it under my square root. So either way is fine, whatever you like best. Okay, number 4, if you're adding, I can only add together like terms. So 6, square root of 6, I can't simplify that any, so that's just going to stay because it's a 2 and a 3. However, 24, if I do my factor tree on 24, I get 4 times 6, and then that 4 is a perfect square, gives you a pair of 2's. So I'd have 2 root 6, and then 4, but then I have a pair of 2's that can come out, and then what I have left over is this 2 and 3, so that's going to make a 6 under the radical. Okay, so now you can see that you have basically terms that match, okay? So they're both root 6's, so I can add those together, and that would be 10 root 6. So just the same concept as if you were doing 2x plus 8x, and that would be 10x. Same concept works with radicals. Okay, number 5, you can multiply. So I'm going to distribute here. This is going to be 3 square root of 5 plus root 5 times root 15. So that's going to be square root of 75. Okay, now since I've multiplied and made this square root of 75, I want to check to see if I can simplify anything. So I'm going to do a factor tree on 75. 75 is 25 times 3, and of course 25 is a perfect square, or you can think of that as broken down into 5 times 5 and then times your 3. So now I have 3 root 5 plus 5 square root of 3. So I could simplify, but even after I simplify that radical, these still don't match. My radicals don't match. I have a root 5 and a root 3, so I cannot add them together. So that's going to be your simplified version. Okay, when you have a fraction, a square root of a fraction, you can think of this as split up into 2 pieces. You can do the square root of the numerator over square root of the denominator. And this one happens to be a perfect square. So square root of 25 is 5. Square root of 9 is 3. And that's all you need to do, 5/3. Okay, number 7, same kind of thing. I'm just going to split this apart so I can go square root of 16 over square root of 3. Well, square root of 16 is 4, and then over square root of 3. Okay, now there's a rule, an algebra rule that says you cannot leave a radical in the denominator. So we need to rationalize. So we're going to rationalize by multiplying by root 3 over root 3. So whatever that radical is in the denominator that you need to get rid of, that's what you're going to multiply by. Because what happens in the numerator, I get 4 root 3, and in the denominator, you get root 3 times root 3. So you could think of that as square root of 9. Okay, but square root of 9 is a perfect square. So this actually simplifies to 4 root 3 over 3. Okay, so that's the purpose of rationalizing, is to be able to get that square root out of the denominator. Just so you can rewrite it without that root. Okay, number 8. Now this one we're multiplying. So again, I can multiply anything together. They do not have to match. They have to match when we're adding. They have to be like terms. But if you're multiplying, they do not need to be. Okay, so we have 3 root 7 times 2 root 21. So 3 times 2, kind of like those coefficients, multiply those together, and that's 6. And then I have 7 times 21 underneath your radical. Now, off the top of my head, I guess it's 147. But if you look at that 21, you know that 21 is 3 times 7. So I already have 1 7. So I'm just going to leave that separated. And then that 21 is a 7 times a 3. So then now that makes that pair that can come out. So 6 is already out front. 7 can come out front now because you got that pair. And then 3 has to stay under your radical. So this is going to be 42 square root of 3. Okay, number 9. Well, those were all square roots. So we were looking for 2 of a kind. But you can also have cube roots, fourth roots, fifth roots. You can have any kind of root you want. So how this would work, this is the cube root of 24. So now instead of just needing 2 of a kind to make a group that can come out, you now need 3 of a kind to make a group. So same concept though, we're going to start with a factor tree. So 24 is 6 times 4. 6 is 3 times 2. 4 is 2 times 2. So you can see here you have a group of 3 2s. So I have enough to make a group. That group is going to come out. And then the 3 doesn't have enough to make a group, so it's going to stay. Now I just messed up on my notation. I didn't leave myself enough room. I have to say that this is the cube root, and then 3 is still under that radical. Okay, so for number 10, same kind of thing. It's a cube. Nope, not this one. This one's a fourth root. So we have to have 4 things that match to be able to make a group. So do a factor tree. Okay, this 4 is a 2 and a 2. This 4, 2 and 2. Okay, so you now have a group of 2s. And then over here, we have a 2 and a 5 that weren't enough to make a group. But that group of 2s is going to come out. This is going to be fourth root, and 2 and 5 are still under the radical. So that's going to go back to a 10. Okay, example 11. So cube root. Now this one also has a variable. We'll talk about that in a second. So 81 is 9 times 9. And the 9s are each a pair of 3s. So we have a group of 3s that can come out. We're also going to have a group of x's. Okay, that x to the 5th means that you've got 5 x's multiplied together. So if I take a group of 3 of those x's out, okay, so these 3 are going to make a group, then I've got 2 x's left over. So underneath this root, I have a 3 that was left over, and then I have an x squared. Okay, that 3 right there, that's for my root. That is not an x cubed. Okay, so there you go, 3x, and then cube root of 3x squared. Okay, number 12, same thing, except this time it's a 5th root. Well, 27 ends up being 3 times 3 times 3. So there's not enough to make a group out of the 27. So the 27 is going to have to stay. But if you look at your variables, you've got x to the 12th. So that's actually 2 groups of x's. So one group of x's will be 5 of them. Another group will be 10 of those x's. Okay, so I have an x squared. So that means out of the 12 that we started with, you have 2 left over under your radical. And then with your y's, if you've got 20 y's, you can make 4 groups of 5 y's each. Okay, so that's number 12. Number 13, again, cube root. So we need a group of 3 things. You're going to be able to find them in 2s. So I'm going to have 2 2s from the 4, and then the 10 is a 2 and a 5. Okay, so this would be a -4. A group of 2s come out, and then cube root of 5 is left over. Okay, I think I'm out of time. So we are going to let number 14 go for today, and you all are going to be working on practicing some of these simplifying square roots.